there everybody, my name is Mike and welcome back to my channel. In this short video we're going to talk about vectors a little bit, run through a couple practice problems. So let's go ahead and get you reacquainted with the subject, or maybe acquainted if this is your first time hearing about them. So this is really for students who are in their vector calculus course, but anyone is welcome to enjoy this because it's pretty straightforward and I think you'll get a lot out of this. So let's dive right in. And let's talk with defining the most simple question. What is a vector, right? What actually is this mathematical object? You know, we know a lot of different math operations. We know mathematical objects like a variable, right? That's an object within math, within the framework of logic that we think about numbers in. That's what we call math. Well, a vector is another one of these frameworks. And a vector, just like many other things in math, is a way to talk about something that we see often in the real world and describe it with a very simple set of numbers or letters or ways to talk about it so that we could write down an idea on paper in a very simple and concise way. So the idea with a vector is it's nothing more than an instruction set. It's an instruction set to get from point A. Forgive me, I'm not that quick of a writer. It's an instruction set to get from point A to point B. That is all a vector is. It is a set of directions. It's like when you ask your friend, hey, I don't know where your place is. Can you give me directions to it? And they send you their address. That's their point in space. And you have your point in space. You plug that into Google Maps. And Google Maps gives you a way to get there. It's a direction set, right? Now, luckily, unlike the real world, there aren't trees and parks and streets and buildings to block us. So we don't have to take all these weird routes to get from one place to another. And in the two-dimensional or three-dimensional space, the way to get from one spot to another spot is just as we call it, as the crow flies. We just go straight there and we draw an arrow from whatever point we want to go to the point we need to go to next. See, if we want to go from P0 or PO, that's the origin, right? We want to go from this point to P2, we just draw a little arrow, and just like that, we're there. That's how we can think of vectors graphically. It's nothing more than an arrow that points, and there's two parts to this arrow, right? Obviously, there's a direction. We've gone from P0 to P2. We've pointed to where it is. But if we made this arrow, let's say, this big, it's the same direction, but, well, notice it doesn't quite reach P2 anymore, does it? So arrows have a direction to them, or excuse me, a magnitude to them, which is what we normally think of as a length, right? A vector has a certain length that it needs to be so that it can actually touch that point that it tries to point to, and it also has a direction, because let's say the vector keeps the same length, but it's down here now. Well, this is about the same length, but obviously the angle in here, theta, it's different, and so it doesn't work either. And so from this we can deduce that you need two parts to make a vector. You need a direction, right? Where do we want to point to? And the second part is a magnitude. You're going to hear this word a lot, and don't let it scare you. A magnitude is just the length of a vector. And we use that word length very specifically because we want to think of these vectors as kind of geometric objects. And if you want to really kind of have fun with it, think of a vector like a really weird triangle where the hypotenuse points to something. So what I mean by that is if I wanted to go from P0 to P1, all right, there's my line, there's my vector. We're going to call this point on the vector V. What I want you to do is think of V here as the hypotenuse of a triangle. And the triangle is going to look something like that. In fact, let's do an even easier one. Let's do this guy here. Let me get rid of you. And let's do from P0 to P2, and that's just so that I can make this nice and big, and you'll see why I did this in a moment. So here, P0 all the way to P2. This is the hypotenuse of our triangle, and here is one leg and another leg. So I want to think about what these points represent and what this triangle represents. So first of all, we've given points, right? We said P0, P2, all this. We don't really know what those mean mathematically, and so let's think about this coordinate system that we're operating in. And every space we have is going to have a coordinate system that we ascribe to it. And traditionally we do X and we do Y in 2 dimensions. And we do this in the real world too. If you ask for an actual location, like you use Google Maps, obviously you spit out an address. You might live at, I don't know, 705 Northwest Place, right? But what you're really telling the GPS is when it looks for that, it the whole world is mapped in a system of latitude and longitude. It's mapped with coordinates, and the coordinates more or less follow a system of x, so plus or minus x, plus or minus y. It's x and y. And we've probably operated within this framework before, so you're probably fairly familiar with it. In fact, you're more likely being able to realize that if I have P2 here, the point at which this point resides, the space in which it resides, that the address within our space here is going to be how far we go from 0 in the x direction, so 1, 2, 3, 4, 4 in the x direction, and then how far we go upwards from 0 in the y direction. And we go, if we start here, this is y equals 0, right? Don't be fooled by the fact that we're over here. This is still y equals 0. And we're going to go 1, 2, 3 to get to y3 right there. And so that's how we describe this point in space, which all should be pretty simple for you, so I won't spend too much time on that. But then what we can do is describe the origin the same way. And if we start here at the 0 point, the origin, that's just 0, 0. So then the vector is going to be the distance pointing from here to here. Now what's really cool is if we think about this as a triangle and we kind of picture everything going on as such, what we can do then is, let's draw our little triangle out here. Oops. Oop. Give it a minute. OneNote's got to come back to it. Come on, buddy. Come on. Please. There we go. We're back. Sorry about that, guys. This is a new computer too. I don't know why that happens, but that's okay. So let's draw our triangle out. Here is the triangle we want to have, and thankfully OneNote makes my handwriting look pretty, so that's nice. And let's see. It's going to go something like this. We have x going 4 here, and y going 3 there. So that's our point in space. That's our triangle that we've represented, right? And what this basically is saying is that if I want to go from this point P0 all the way to P2, right, I'm going to go 1, 2, 3, 4 in the x direction, and then 1, 2, 3 in the y direction, and bam, I'm there. And it works in other ways too, which is really cool. You don't actually have to keep that order, right? So let's say I start at 0 and I go this way. I go 1, 2, 3 in the y, and then I go 1, 2, 3, 4 here. I reach the same point 4, 3 in either situation. What matters is that I have x in front of y like this. And if you do that, it doesn't matter how you add to get there. You could do x and then y, or you could do y and then x. In either situation, you'll arrive at the coordinate point 4, 3. So we can describe these as legs on our triangle, which means that we can then figure out the length of a vector just by thinking of it as a hypotenuse. So the length of this vector, well, if you're familiar with triangles, 3, 4, and 5 by the Pythagorean theorem is going to give us a hypotenuse of 5, right? 3, 4, this is a 3, 4, 5 triangle. So we are actually able very quickly that way to then deduce the length of this angle. And that just tells us that if we were to stick a ruler here, the measurement we would get is 5. And that's 5 units in whatever we have here. Maybe this is centimeters, feet. You know, in math you might just have an abstract like the length is 5. It is what it is. It means whatever it could mean, however we choose to apply it. So that's the kind of the basics of vectors here, is that the vector is going to have a length, and then the direction is usually given within those components. And so it may sound silly because you might see this triangle, right, that we've described here, this direction set, which is a set of instructions that tells us how to get to a specific point. And you might think to yourself, how on earth do we have direction out of this? Because a lot of times people will talk about direction and they'll say you'll have an angle in here, theta, and that angle is the direction. Well, yeah, this is true, but what's really cool is that we can also get that angle implicitly. If I have a triangle and I know all 3 sides, A, B, and C, woo, I gotta turn off ink to shape. If I have A, B, and C here, then I already know every angle. Because as long as this is a right triangle, and they always will be, because that's the nature of our coordinate system, then trigonometry will always give us any angle we wish to find. So what that means is that if I give you the components here, and if this is our x-axis, right, then I say we go 4x, right, so 4 in the x direction, and now we're going to write this in vector notation. So we have 4 for the x direction and 3 for the y direction. Then what we've given you are the legs of a triangle, and you can find the hypotenuse just as we would do with a triangle, right? So we would just take the square root of 4 squared plus 3 squared, and that's c squared, right? That's equal to c squared, or I guess in this case, since we have that square root, that's just equal to c, and that's our Pythagorean theorem. So the same applies here for the vectors, and that gives us the magnitude of whatever vector we like. So in this case, now we have the side lengths and the length of the hypotenuse. We could then discover whatever angle between the two vectors very easily just by doing some basic trigonometry. So if they ask for direction, there's two ways to do it. One is you give them the length of the hypotenuse and then the theta in here with some trigonometry, or you can just give them this guy and that'll tell you both. Now usually if you're asked for direction, they'll probably want you to give theta, but just know that that's why we say that this has both direction and magnitude, is that implicit in this vector is a direction that you can always derive algebraically with a little bit of trigonometry. So that's the basics on vectors. Now let's get into some kind of problems where you might encounter vectors. And so let's start with this first example here, and it's sketching vectors. So it says sketch a vector in the plane, and when they say in the plane, they just mean this screen. This screen is your plane, whatever you're watching it on right now. That is a plane, like a sheet of paper, and we're sketching something on it. So don't get hung up on the nomenclature. Sometimes these books like to make themselves extra complicated, and I've yet to figure out why. But we're going to go ahead and create a little plane here like this. And it says, or rather a little coordinate system, and it says sketch a vector from initial point P, which is at 1 and 1, going to terminal point Q, 8 and 5. So I guess I probably should have made these guys bigger, but that's okay. We'll make it work. Let's go 8 in this direction, right? So remember, the way this works is we have A, B, right, in our vectors, which correlates to X and Y, and X and Y. That means the first part of our vector, or in this case, these are points, right? So that just means the x component of the point and the y component of the point. Vectors will follow the exact same notation. So if I have a point AB and I have a vector BC, which are two unrelated quantities, it just should note that in both situations, right, because mathematicians are organized people, in both situations, x represents the first quantity and y represents the second part there. And if you actually did end up having a third component to this, what do you know it, z here, or I guess if we're following our format, d is going to represent the z direction for 3 dimensions. And you will get into it on this course, and later on in the videos here that I'll do, we'll talk about that, and it gets very fun, I promise you that. But then let's go ahead and just write all this out. So here's P at point 1, 1, which I just went over 1, up 1, and then terminal point 8, 5. So let's go starting from 0. We always start at the origin. We're going to go 1, 2, 3, 4, 5, 6, 7, 8. This is 8 in the x direction, and then 1, 2, 3, 4, 5 in the y direction. So here's Q at 8, 5. Lovely. Now, it then says to sketch a vector between these two. So hopefully you can kind of have an idea of what we're going to do. It's super duper simple, and don't let yourself overthink it. We are literally just going to draw a line connecting the two, and this right here is our vector. Now remember, we can also think of it as a triangle here. And so let's go ahead and do that for a minute. There's the legs of our triangle. If we draw a rough triangle here, do you have any idea what the length of this vector might end up being? What is the magnitude of V? Well, we can figure that out pretty easily. But notice that our triangle isn't going to be 8, 5, right? This side length isn't 8, and this isn't 5. Well, why is that? And that's because we don't start at 0 here. So let's actually count how much the height and the width of the triangle is. So if I count this, I have 1, 2, 3, 4. I have a side length of 4. And 1, 2, 3, 4, 5, 6, 7. I have another leg of 7 there. And of course, remember, since we're working within these two directions, we only have these two directions and they're perpendicular to each other. We'll always have 90-degree triangles in this, so you can always use trigonometry. But since we discovered what these side measurements are, since we counted them, you might notice an interesting trend, and that is that the side length here, 4, what's that equal to? That's equal to this initial point Q in the y direction, right? So 5, we call that QY minus whatever we started with in P, so PY. Or what's another way we could write this? 5 minus 1, because P was 1 and 1, right? So you can try this for any pair of points. For any pair of points A and B, where A is ax, ay, and b is bx, by. We're generalizing what we're doing here. So I want you to imagine P represents A here in this generalization, and Q represents B, okay? Just so you can kind of get an idea of what we're doing here. We're trying to find the general case. For any points A and B, what we're going to have is the side lengths here are going to be, we're going to say side lengths of the triangle. This is very, very great nomenclature, but just roll with me on this, are going to be bx minus ax and by minus ay. Now this will always give us the side lengths for the triangle. Now those are very useful because these side lengths for the triangle serve a very important purpose. And that's not just that they're side lengths, but they are also the descriptors, right, the components of our vector v here. And that's because v is an instruction set, and it tells us how to get from P to Q. It doesn't tell us how to get from 0 to Q. V tells us how to go from whatever point we start at to our endpoint. So let's count that. We have 1, 2, 3, 4, 5, 6, 7 in the x direction, and 1, 2, 3, 4 in the y direction. So v as a vector is also described with these side lengths because it's just an instruction set. So if we wanted to then write v in component form, we would say v is equal to, well, how far did we go in x? 7. How far did we go in y? 4. V is equal to 7, 4. And remember again, we have x, y. That's the format we always follow. Why? Because that's what points do, and we want to keep things simple. So it's always x and y. So v is equal to 7 and 4. Furthermore, we can even calculate the length because remember, we're relating all of this back to triangles. V, our vector here, is nothing more than the hypotenuse of a triangle made up of the components of V. So that means, what is the magnitude of V? And you'll see this symbol a lot. They just do two lines. It almost looks like an absolute value because it kind of is, right? I mean, if you have a vector and it's got a direction, if we take the direction out of that vector and we just want to know the length, it's kind of similar to taking the absolute value of a function, where if you imagined, here's our number line, right? And I have -1 here. Well, if I just wanted to know the absolute magnitude of 1, what would that be? That would just be 1, right? Because that's the overall length of the one-dimensional vector, which happens to be the number -1. So that's all just tantamount to it. It's just fun to think about. But what we want to do then is take the magnitude of V, and since we're operating in 2 dimensions here, we need to treat this like a triangle, which it is. So we do the square root. What's the Pythagorean theorem? A squared plus B squared is equal to C squared. So the square root here gives us C. The square root of A squared plus B squared, which is equal to, and it doesn't really matter which one of these is A or B, although if you're being, somewhat nice about it, then you might just say that A is first, so we'll use X because X comes first, so it's 7. So 7 squared plus 4 squared. And, you can follow this out and get an actual answer for V here, but the key to understand is that, actually, let's go ahead and do that just so that I can try and be nice about this. So you get the square root of 49 plus 16, which is equal to square root of 49 plus 16. That's equal to about 8. So that is the length of V, the magnitude of V. So we can say magnitude of V. And now it didn't ask for this, but we're going to see questions later on that will ask for this. And it's very useful too. Sometimes we might want to give the total amount of force that something has. If you're an engineering person or an engineering major in college, you might be asked to find the net force of something. And so you've got 2 forces coming down or pushing into something. And we don't really care where the forces are coming from. And this isn't going to be too helpful for us. We just want to know how much force is actually being applied. And so that's what this number does, is it just tells us the overall length or force or total sum of things that's going on within a vector. And so it's just 8. So that's how we sketch something, and that's how we describe the vector. We'll go ahead and call this example done. Let's look at another one here, and this example is super simple. It's just talking about equivalent vectors. And so this is one that a lot of people kind of screw up starting out. So you might see something like this and say, Well, they're all different because they're at different points in space. But remember that a vector is nothing more than an instruction set, right? So that means that a vector will tell you, starting from a certain point, you're going to go a certain number in the x direction and a certain number in the y direction, and you'll end up at your endpoint. So what we want to find are vectors that have the same directions, right? So let's look at D and compare it to B for a minute. And if I look at D here, this vector D, I go 1, 2, 3, 4, 5 in the x direction and 1 in the y direction. So if we wanted to write D out numerically, we might say D is equal to 5, 1. And I'm using those angular brackets as vector notation. That's different than a point, right? A point has the regular little brackets, angular bracket, or the parentheses, excuse me, and a vector is going to have your angular brackets like that. So D is 5, 1 because that's the direction set. Notice that actually has very little to do with the actual point where it sits. It starts at -1, 1, and we go to, 4 and 2. And we talked about this, remember? If you took the initial point and the end point and you subtracted the end point, so let's see, for x we have 4 minus -1, and we end up with 5. And that's how many x we move over. So you can see there that the legs of the triangle are actually the components of the vector, just like we've done before. So D is 5 and 1. Let's compare that to B. B goes over 1 in the x and up 2 in the y. We jumped left by x. And I got to try and remember that I drew the arrow the wrong way. If you're being very technical about this, actually, yeah, we are moving right, so be careful about this. It almost caught me because it's a little late at night right now, but we move to the right here. See where this arrow points, right? If I drew the arrow this way, then the big arrow, whatever we added to, would have to look like this. But it doesn't, so just watch out for that. We start at our initial point, whatever this is, it almost doesn't matter. And we go this way in the x direction, which gets us on the same plane as our y point here, and then we go up to get to the exact same point, right? So one step, one little mini movement here gets us to the same line. We share the line with the point we want, and then one more gets us to the exact point. And if you do that, obviously we move 1 in the x direction and 2 in the y direction, so we can call B 1, 2 with the angular brackets, and that denotes vector B. So you might figure out now, okay, well, if we know what this vector looks like, then we can also figure out pretty quickly, hey, A is that exact same instruction set. E is that exact same instruction set. Does C? It does not. Let me pose one more question for you. If I have a vector that looks like this, we'll call this vector G. Is G equivalent to these guys? And the answer is no. No, G is not. In fact, let's do 2 more. I'm going to add G, and then I'm going to add one more vector here. And this will be vector, ooh, I'm bad at drawing, you guys. This will be vector D. I'm trying to get it away from all the other ones. There we go. That is vector D. Is D equivalent? And hopefully you're pretty quick in spotting this. The answer is no. Why is D not equivalent? Well, you're probably looking at this and you're thinking, well, I mean, it points the same way. You've gone over one some way in the x, and you've gone some direction in y, and both of those are 1 and 2. But the difference is that we've gone down here. And so this is where the direction part plays a key role. When you have two vectors that have the same direction, right? We've done the same thing in both. We've gone a certain x by 1 and a certain y by 2. That, and when I mean we've gone a certain way, is that I mean we could have gone up y, we could have gone down y by 2. Something's happened here, and in the case of this vector down here, we just did negatives of whatever we did. So we went -1, -2, and what we get is that these two vectors, your intuition is right, they are related somehow. The vectors are parallel, and so if we wanted to describe that in math, we might say that A is parallel. Those two lines mean parallel. A is parallel to D. Parallel, but not equal. We would not be able to say that A is equal to D. They are not the exact same. The way that a vector is the exact same is it has to have the exact same magnitude, the same length, and the same direction. So another example of something that wouldn't quite be parallel or wouldn't be quite equal to is, let's say E actually went all the way up here. So we'll just continue to draw this line out, and let's say this was E. Well, now we would have the same direction. Look, we would have, and actually what's really cool is I could superimpose this onto A, and you can see it's the same direction, but they're not the same length anymore. And so, again, you have a situation where we would say A is parallel to E, but they are not equal. So in order for a vector to be equal, it pretty much has to, you have to imagine this a little bit, and vector calc is really one of those classes where the more you can cultivate your ability to visualize things, and it's something you learn, so don't worry, but if you can visualize something, it'll help you a lot. The best way to picture this is if we take a vector and just place it on it. If we can copy the vector over and it looks the same and it fits right in where it should, then the vectors are equal. If they can't, or you have to rotate it or do anything to the direction or the length of the vector, then they're not equal to each other. Okay, one final, we'll do two more and then we'll head you out of here because this is a long video now. But this is going to be vectors, and we're going to talk about a very simple one here. It says vector W has the initial point, -4, -5. There we go. And it has a terminal point somewhere up here, -1, 2. There's no coordinate system here. I'm just kind of making things up, so apologies in advance. But we just have something here, and obviously we've got a vector right here. And I like to think of it as a triangle again. And we have a side A and a side B and a side C. And it actually gives us the side C. We said the name of that side C is W. Vector W. So let's do what we did before with our little triangle method. And what did we say the length of this triangle was? What did we say the side lengths were? We said that if I wanted to look at this side, right, this is the change in y, and that's another way we can write this, is we could say this is delta y, and that means the change in y. And what is the change in y? To go from the starting point P0 up to P1. What did we do to get there? Well, we started here at y equals -5, and we went all the way up to 2. So my question for you then is, if we wanted to talk about this, we can actually make a really, really simple equation for this. We can say that -5 plus a is equal to 2, which is true. If I move this guy all the way over and I put our point here, obviously x is different now, but y is still -5. So -5 plus a is equal to 2. What is a? And you can solve for this very quickly, probably just by looking at it, and you see that a is equal to 7. I really hope I did that right. It's getting a little late. Yeah, a is equal to 7. So that is the side length here. And let's do the next one. Now remember, this is all in the y direction here. So delta y is equal to a, which is equal to 7. That's what I meant to say. Let's do one more in the x direction here. So starting at -4, we go to -1. So we say -4 plus a, or this is plus b, excuse me. -4 plus b is equal to -1. And very quickly we can say this is probably going to be, we can actually just move it over. So +4 both sides. And b is equal to 3. Now remember, this is for x, for x, and this is for y. And that means that the vector here is going to be w is equal to the x first, which is 3, and the y component, which is 7. So that's how we can express w in component form. That is the total bit of our vector here. And we can check our work super simple. So let's go starting at P0, -4 plus 3, which is from our vector here, and -5 plus 7, which is also in our vector here. What does that give us? That's going to give us our final point. -4 plus 3 is -1, and -5 plus 7 is 2. And that's our final terminal point. So that means that our vector worked. This is our instruction set. And we followed the instructions, and what do you know it? We got to where we wanted to go. So our vector worked there, and we've expressed w in component form. This is going to be one last one here, which is finding a unit vector. We're going to focus on this guy in a later video just because I don't want to keep you too long. And this is finding a unit vector. So it says let v equal to 1, 2. And so again, this is a vector. You can tell by the angular brackets here. So v is equal to 1. Now remember, positive is always to the right, and positive is always up with the y, right? So we're saying v is equal to go positive x, 1, and 2 in the positive y. So 1 and 2, that's our kind of like triangle here. So there's 1, 2, there's v. So it says find a unit vector with the same direction as v. And we haven't covered unit vectors very much, so let's just very quickly go over them. A unit vector is the idea that maybe sometimes we want to talk about the direction purely. I mean, you know how to describe something just in length, right? We say that a vector is length and direction, or magnitude and direction. So if I wanted just to describe something in terms of magnitude, the traditional example always is to give speed. It doesn't really matter where you're going. If I say I'm going 30 miles an hour, that's my speed. The only way to know my velocity is if I tell you I'm going to go 30 miles an hour east, right? Well, what if I just wanted to tell you mathematically that I was going east? Well, let's think about this in algebra. If I wanted to have a quantity 3, and I wanted to keep the overall amount of that quantity 3 the same, if I multiply it by 1, 3 times 1 is still 3, right? So how does this relate to vectors? Well, if I have a quantity v, a vector quantity, which is what these things are. These are direction sets, yeah, but it's also a way to represent an idea. It's a quantity. V has two numbers that go into it, and I want to make sure that the direction scales but stays the same. This direction should always be some bit of 1 and 2. So I should always, like if I were to scale this triangle, right, then I would want to scale it such that we can do this too, actually, which is really cool. Thank you, OneNote. We can scale it such that the triangle would be 1/2 and 1. Maybe that's closer to what we want. But what we really want is a triangle that has a hypotenuse of length 1. And if you have a hypotenuse of length 1, what that means is we have now something that's purely the directional equivalent. And this is more useful for when you get into things like the dot product. What you need to know right now is sometimes it's useful in math to describe just the direction of a unit vector for no other reason than to describe where something is headed regardless of its direction. Because maybe you don't know the exact magnitude of the force, right? If I have a catapult like this and I want to launch a ball this way, I might not actually know how much force this catapult's going to create, but I might need to know what direction I need to shoot the ball so that I don't hit a bird or hit a building some 400 yards away. So sometimes direction is important, but magnitude isn't. And when that's the case, we want to describe direction purely. And so the way to purely define a direction is super, super simple. If I have this triangle, let's do an example, okay? Let's say I have another triangle, and it's a 3, 4, 5 triangle. And I want to scale this triangle down to a side length of 1 here. What would I do? What would I do to this triangle? What would A and B be? This is super simple, so don't overthink it. To get from 5 to 1, I take 5 and I divide it by 5. It's that simple. That's 1. So let's do that for the whole triangle. In order to scale a shape linearly, everything needs to be the same. So 5 and 5, and I'm going to scale this up. This isn't technically 1 anymore, but let's pretend that the triangle, you've got a little you've got a magnifying glass, and you can see the triangle a little better now. So 5 and 5 here is 1. 5 divided by 5. We're going to do the same for all the other sides. 4 divided by 5 and 3 divided by 5 gives you two sides, which when you do the Pythagorean theorem of square root of 4 over 5 squared plus 3 over 5 squared. You can do the math as a check just to make sure you can understand it, but if you do this and you do the square root of it, you're going to end up with 1, which is super duper cool. So this is a very simple way to scale any triangle down, and since we've already kind of discovered that vectors operate or can be thought of a lot like triangles, then we can use this same technique to work within the confines of the unit vector. So how does this unit vector work? Well, let's say instead of a length 5, I have a vector of length v, all right? And here's v right here, the magnitude of the vector. And remember, that's all those bars mean. Those bars on either side mean we just want the length. We don't care about direction, it's just the length. And on each side here, I have the vectors, I have vy and vx, and those are the x components and the y components of our vectors. If I wanted to get a unit vector of v, all right, all I would do is, well, we want the side length, we want the hypotenuse is just 1. So just like 5 over 5 before, we'll do v over magnitude of v. So that's equal to 1. And each of these sides, we're going to have vy over v, magnitude of v. Over here, we're going to have vx divided by the magnitude of v. And remember, the side lengths make up the components of our vector. So if we wanted to then describe the unit vector of v, and uv is just our little shorthand for talking about the unit vector, we would describe it as, well, the side lengths here. So starting with x, like we always do, we'd have vx over magnitude v, vy over magnitude of v, where the magnitude of v is the original side lengths here. It's just the square root of vx squared plus vy squared, just like we did before using the Pythagorean theorem. So let's go ahead and do a test, and I'm going to delete this last guy because I don't think we have time for it. I don't want to make a 50-minute video. So let's go ahead and describe the unit vector here. And v is equal to 1 and 2, right? So let's do this. V is equal to 1, 2. So the first thing you should do, step 1, is you want to find the magnitude of v. So let's do that. The magnitude of v, remember, if this is vx and this is vy, then the magnitude is the square root of vx squared plus vy squared. And that's just the Pythagorean theorem because, again, vectors are triangles. Say it with me. Nail that into your head. Trust me, vector calc is easy if you just remember that. So find v. Well, it's going to be equal to the square root of 1 squared, which is 1, plus 2 squared, which is equal to 1 plus 4, which is equal to the square root of 5. Now this is the magnitude of v. So look back at our formula here. Let's go ahead and apply this. We have vx and vy, and we have the magnitude of v. So starting with the first component here, vx over magnitude of v is 1 over square root 5. The next step, for the x component, we have vy over magnitude of v is equal to 2 over square root of 5. And so the total unit vector for this guy, uv, is equal to, remember, x and y first. These are the new components of our unit vector. And so now this guy right here, we could almost think of it as ux and uy. So x component first, 1 over square root 5, comma 2 over square root 5. See how simple that is? And all we're doing is taking this vector and just scaling him until just the length is 1. That's all a unit vector is. It is a pure statement of direction. And if the magnitude is 1, then anything we multiply here doesn't actually get affected. It stays the same, but the direction is altered. So that is the premise of a unit vector. And with that, I think our video is long enough. I'm almost begging you here, if you have any questions, please leave them down below in the comments. The best way for me to help you is if you ask questions and I can answer them. So thanks so much for watching if you made it this far. Please like and subscribe if you care about any of this or if you want to learn more. I'm always open to suggestions for videos, and I'd love to help you get where you need to go in math. So you guys have a great night and good luck.